Yeah, thank you everyone for being here. I hope everyone is safe and sound. And today I'm going to talk about vegetation canopy structure in Earth system models. A part of this presentation is going to be about the latest paper we published, so 2 months ago, and it's going to be physically published in a week. So I thought it was a good time to talk about that. But also, I want to talk about Earth system modeling in general, where we are coming from and where we might go. So let's dive into that. So I like to start my presentation with these two figures, and now we have the updated version, right? So Aurora et al. Just published this paper earlier this year. So what these figures show is basically the land uptake from 1850 to the end of this century for 11 Earth system models in the CMIP exercises. And so what we see is that since 2006 and then again in 2014, and apparently it keeps doing the same thing this year, the Earth system models, they disagree not only in the magnitude of the land uptake, but also on the sign of the land uptake. So they even disagree if the land will remain a carbon sink by the end of the century or become a carbon source. And when we see this comparison between the two CMIPs, so 4 and 5, we see, well, it doesn't look like the spread of the models is decreasing. And when we look at the 6, we kind of like also have this disagreement in magnitude and sign. Another way to look at this question is kind of like look into the global carbon budget. And these figures here I took from the one last year, so the most recent one. And basically what we can see here is the CO2 flux partitioning. So the anthropogenic CO2 is emitted as fossil fuel in industry and land use change. And then the CO2 that is emitted, it's split into 3 Earth components. So part of this goes into the oceans, part of this goes into the land surface, and the remaining bit stays in the atmosphere. And when we look at this figure here, we see that the component that is responsible for most of the interannual variability in CO2 uptake is the land surface. And of course, the ocean and the atmosphere are also very complex to model. But these two components are physical components, while the land surface is this biological carbon pump where we can see a lot of different processes. So plants interact with different living beings on Earth, and this type of processes are very hard to model. Another way of looking into the land sink is to say that anything that doesn't go into the oceans or doesn't remain in the atmosphere is probably being uptaken by the land surface. And so often what these exercises do is to run land surface models, the land component members of those Earth system models, and take the ensemble mean, so the green line here, and compare the ensemble mean with the residual budget. And then what we see is that along the years, it looks like the ensemble mean is agreeing pretty well with the residual budget. However, I want to call your attention for two different things in this plot. The first one, it looks like the residual budget and the ensemble member are disagreeing in the last few years, or at least that they are not right on top of each other. And also another thing that I want you to pay attention to is the spread in the result of individual members. So while for some years we have models that say that the land surface is acting as a strong carbon sink, other models say that the land surface is a carbon source. So I'm not saying that this disagreement between land models is necessarily a bad thing. Of course, these models are representing different things, and so it is expected that they have different answers for that. And then we, as scientists, expected the truth is within this range. However, it would be good if these models give us assign a unique and truthful answer, at least if the land surface will behave as a carbon sink by the end of the century. Because our political agenda depends on this. So for example, in the Paris Agreement, when we have the 2-degree target, we have to make some choices, how much we should we emit this year or next, and we depend on the certainty of the land surface keep acting as it is. Otherwise, we might have wrong or not so certain political decisions. So why is that? Why did these models disagree so much among themselves? And I took this sentence here from the latest IPCC report. And basically, what they say is that processes are missing in terrestrial carbon models. So in this plot here, we have the residual budget sensitivity of land sink to the interannual variations of precipitation versus temperature. And as we can see, these land surface models here are all around the place. So most models say are too sensitive to precipitation interannual variations. And most models are not so sensitive to temperature. But the IPCC is blaming the missing processes. So there are not enough processes represented in these models. So what are these missing processes? What is the IPCC saying that these processes are? So the IPCC starts saying that disturbances or ecosystem dynamics is the first one. So things like migration and fire. But again, if we think about the CMIP6 members, most CMIP6 members now have some sort of migration or fire in them. Then decomposition of carbon. So how carbon decomposes in soils. So, some models have 3 carbon pools. Other models have 25 carbon pools. Why? And different models are trying to represent different things. And that's why they take different decisions. Then nutrient dynamics. Everyone was talking about nutrients. So if we add nutrients, we're going to get a better result. And the thing is that now the CMIP6, if we compare with the CMIP4, now the CMIP6, most models have nitrogen dynamics in them. And some members even have phosphorus. So we are adding nutrients into these Earth system models. And then a number of different things like tropospheric ozone, mycorrhizae representation, and so on. And this figure here that I took from Gordon Bonan's book from last year shows the number of equations in CLM. So from 1980 to CLM 4.5, CLM 5 is probably somewhere up here. And what we see is that if the number of equations in this model is actually increasing almost exponentially, right? So new processes are being represented in this model. And this is only one land surface model. If we think that the number of equations in all these land surface models have been increasing with time, probably we are doing a relatively good job in representing different processes. So it kind of looks like complexity itself is not the problem. So I took this picture here from Rosie Fisher's paper. And basically what we see is that the evolution of land modeling. So surface energy fluxes was what these land surface models were doing by in the 70s when they started. So because these land surface models usually were built to behave as the boundary condition or the lower boundary condition for the atmosphere. So all we needed to do in the 70s was giving an albedo or some sort of water representation. But along the years, more and more processes have been introduced into these models. So lakes and rivers, the carbon cycle, land cover change, urban surfaces. Now we even have, I was working with U3SM the other day, and they even have a representation of the heating from air conditioning from cities. So we are actually representing a lot of things in these models nowadays. So when we talk about the revolution in land surface models, we really think about the greening of ESMs. So when we start looking at land surface models as not this, this boundary condition that only it has an albedo that sends some energy back to the atmosphere, but rather an active biological carbon pump with a Calvin cycle in it. So now we know that if plants photosynthesize, we are probably missing a huge component of the global carbon cycle if we don't consider photosynthesis. And again, photosynthesis, when we think about photosynthesis modeling, we think about the Farquhar, von Kamira, and Berry photosynthesis model. And the Farquhar model is actually a very nice model because it works very well for leaf photosynthesis. So we take a leaf clipper like this one and we vary the intercellular CO2 and we might have a nice response from the net CO2 assimilation. And then the same way, if we vary light if we vary light, we can also have a response. So basically the Farquhar model works as the co-limiting regime from two limitations. It can be carbon limited or it can be, photosynthesis can be light limited. And these models works super well for leaf photosynthesis again. But, so I had the privilege to go to the Amazon during my master's degree, and I took these two pictures here. So the one on the left-hand side, it's me on the top of the flux tower. And when we look at the horizon, we see this massive green carpet. And we might think, well, yes, it looks like a big leaf, like a huge leaf from up here. However, the second picture was taken from below the flux tower. And we see that, no, the Amazon doesn't look like a big leaf from below the flux tower. We can see leaves that are oriented, they have orientation, they have shapes, the canopy has some gaps, so we can see that light is coming through more efficiently through one part of the canopy, not the other. We have a vertical distribution of things. So there are a lot of different things going on here. And the second reason is actually the fifth reason that the IPCC report names there for, the disagreement between our system models is this one, and I quote, transfer of radiation, water, and heat in the vegetation soil atmosphere continuum are treated very simply in the global ecosystem models. And when we think about the transfer of radiation in these Earth system models, and here I'm going to talk about radiation, but we can think about water, momentum, and so on. We need something that is, one, efficient, because we want these models to run for many, many years, centuries, over the entire globe. So sometimes we have our system models running with 25 kilometers spatial resolution. So we are actually talking about lots of data. So we need a radiative transfer scheme that is fast and accurate in somehow. So the two-stream scheme that we use in our system models is the Sellers scheme. So this paper was written in 1985, and since then, most of our system models have used this radiative transfer scheme. It's a good scheme because it has different treatment for direct and diffuse radiation, and it accounts for all orders of multiple scattering. And it gives us all the three members of the radiation partitioning. So it gives us absorbed light, so we can calculate photosynthesis. It gives us reflected radiation, so we can calculate albedo. And it gives us transmittance. So the idea, this model is quite efficient, and it is a good approximation of what's going on. We have to make some assumptions. And the assumptions we make when we use a model like this one is that the canopy, a vegetation canopy, looks like this. So it's a cloud of phyto elements, very tiny phyto elements. And the two-stream scheme was actually written for nebulas, the radiative transferring nebulas. So we are talking about particles. So is this approximation good enough though? And then I want to talk about vegetation canopy structure. And I really like this picture because we can see the radiation coming through and actively interact with the canopy structure. But canopy structure can also impact canopy water interception and momentum fluxes. And the thing is, when we read papers that talk about canopy structure, we don't see an agreement between these papers, among these papers. So what we see is some people talk about canopy structure and then they are simply talking about LAI, or leaf area index. Is leaf area index a good representation of canopy structure? Yes, but is it the full picture? No, probably not. And then another, even in here, the Carbon Club, other people were talking about canopy structure, but then all they are talking about is leaf angular distribution. Is leaf angular distribution canopy structure? Yes, but is it the full picture? No. Or even JEDI. Let's think about JEDI now. JEDI is measuring the vertical profile of LAI. Is the vertical profile of LAI canopy structure? Yes, but is it the full picture? No. So that's why I thought it was interesting to bring a definition of canopy structure from Norman and Campbell, as old as me, that says, and I quote, "Canopy structure may be thought of as the amount and organization of above ground plant material, which might include size, shape, orientation, and positional distribution of various plant organs such as leaves, stems, branches, flowers, and fruits." So when we think about canopy structure, we really should be thinking about the whole picture of what canopy structure means. So let's have a look at direct transmittance in these canopies, right, in our system models. Direct transmittance is the easy brother of the radiation partitioning members, and something that JEDI measures. So JEDI is measuring P-gap as well. So the direct transmittance follows an exponential decay of LAI, or the optical depth of this canopy, divided by the cosine of theta, that is the incident angle of the radiation. And then we use a K factor, and this K factor is the light extinction coefficient, or whatever you want it to be really, which tries to account for some level of canopy structure. So K can be thought of as the leaf angular distribution function times a clumping index. The leaf angular distribution function is in most Earth system models nowadays. And although they use a randomly distributed, usually they use a randomly distributed leaf angular distribution for the whole globe, but we can see how leaf angular distribution can impact direct transmittance and radiation partitioning. So if we look at this picture here, we see that horizontal leaves absorb more than if the leaves were vertical. And then what are the impacts of that for P-gap? Well, direct transmittance goes to 0 much faster if the leaves are horizontal and slower if it's not. There's also a difference between sunlit and shaded leaves. So when we calculate photosynthesis, we might want to take that into account. So JEDI is also using a leaf angular distribution, but they also assume that the world has a random leaf angular distribution. Now, clumping index. The clumping index is this factor that talks about how much a canopy is clumped, or how much space you have in between trees or within trees. So any sort of canopy gaps you have. So for example, in this case, we have large gaps, and it's 0.42, and then smaller gaps 0.49. The difference is not huge here. But the idea is that the clumping index is going to be equal 1 if we're talking about a homogeneous case. And JEDI is also using a clumping index of 1. So I just wanted to bring that here because when we use direct transmittance from these models, or when we're going to use, for example, LAI from JEDI, we might want to think that there are assumptions of a homogeneous canopy going on as well. So one exercise that I did a couple of years ago was, okay, so if LAI is the truth, so what is actually taking vegetation structure into account? Let's do the following exercise. Let's take 4 different canopies, okay? All of them have the same LAI, so LAI is equal 1.5 here. And one is the two-stream case, the two-stream scheme, the homogeneous canopy case. And then we decrease canopy cover. So here the dense canopy cover has 50% vegetation cover, the median 30%, and the sparse 10%. And how do we fix LAI? So well, in the sparse case, one sphere has a lot of leaves inside. So the sphere is very, very dense. And then in the dense case, it's less dense. And what we do, and what we see when we run this 3D model, so I ran a 3D radiative transfer model. And what we see here is that by holding LAI constant, the error we make when we don't consider canopy structure can be huge for FAPA that drives photosynthesis and for albedo PAR that drives the energy budget. And so, and it's not like it's only at, zenith angle equals 1 or only for direct radiation. No, we can see this difference across zenith angle values. And iso here means that the radiation is diffuse. So the radiation is isotropic, coming from all all orientations in the sky. So the idea of the clumping index is, can we then multiply LAI, right, by a number, by a value, that can actually make this curve from the two-stream scheme matches the one from the 3D model by simply multiplying, by simply using a value. And then a question is, how does this value look like? Is this a single value for a different canopy? Or we should also consider other things when we take clumping into consideration. And again, we are not changing LAI in other parts of the land surface model. When we're going to calculate photosynthesis, LAI is going to be held constant. However, what we're doing is we're now using an effective LAI to calculate radiative transfer. And again, we can think about this effective parameter to think about momentum flux or water interception and so on. So there are 2 models that I compare in the paper. One model says that the clumping index is dependent on the incident radiation or the angle of the incident radiation. And the other model says that we do not depend on zenith variation. So it doesn't matter the incident radiation, the clumping is the same. The idea behind this model here, the first one, what I call Pinte, is that if the radiation beam is crossing the canopy, it's interacting with some sort of structure that is different from if it was reaching the canopy from another angle. So in other words, the structure changes with zenith angle as well. So how did we test that? So basically, the way we tested was we compared 2 sites, okay? One, it's a dense old aspen site in Canada, and the other one, it's a sparser blue oak savanna in the USA, here, Tomsey Ranch in North California. And basically, in these 2 sites, we had digital hemispherical photographs not randomly, but sample across, all over this canopy. And what we see here, this is an example for the blue oak savanna. So All we need to do is to have a fisheye lenses and a camera, a good camera, go to the field, point that up, and take a picture. And then we're gonna see something like this, okay? The hemispherical photos have to be taken either sunset or sunrise or in an overcast position because it's overcast situation because we really want the sky to just be a background. We don't want cloud interference or anything like that. And then what we're gonna do is we're gonna threshold this picture into a black and white picture. And we're gonna say that whatever is black is canopy and whatever is white is background sky. And then we are going to calculate the P-gap, so the average in all zenith angles, right? So the zenith angle profile of a hemispherical photo is thought like this one. So the zenith equals 0 is here in the middle of the photo. And as we go towards the border of the picture, we increase the zenith angle, so it goes up to 90. And then what we do is we have the zenith variation and we have the azimuthal variation of this canopy. Then we take the average, the azimuthal average, and we can have a P-gap, so a direct transmittance zenith profile in this gap. So this is how we took the measurements for the hemispherical photos. For the 3D modeling, what we did was two different ways. So for the old Aspen side, there were actually dendrometry measurements. So actually people that went to the field and measure each tree, the position of each tree and so on, in a 60 meters by 50 meters area. And we recreated this area in the 3D model. And for Tulsi Ranch, there was a LiDAR flying over this and algorithms were able to take the canopy structure. This red element you see here, that looks like a red tree, but it's not, is the flux tower. And the flux tower for the old Aspen side is around 50 meters this way. So when we compare now the P-gap from digital hemispherical photos in dashed black here, the dashed lines, with the 3D model, MAESPA in red, we see that they agree pretty well for the dense side and for the sparser side as well. Now, when we look at the P-gap or the direct transmittance that was calculated by the two-stream scheme, we see that for the dense side, the two-stream scheme underestimates quite a lot direct transmittance. And somehow for the Blue Oak Savanna. So what do we do with that now? So now what we did was to derive a clumping index that varies with sun zenith angle, called Pinty, or that doesn't vary with sun zenith angle, called Nielsen, for the model P-gap, sorry, the measured P-gap. So this was the P-gap from digital hemispherical photos. And when we apply the model that varies with sun zenith angle, we get a much better agreement than the one that doesn't vary with sun zenith angle. Oh well, but one might say, well, of course you have a better agreement with the one that varies because you have more free parameters, and a model with more free parameters will fit better to the data, right? Well, that's why we calculated the Ikaike information criterion, which is then a statistical tool to kind of evaluate the parsimony of models without taking into consideration how many parameters the model has. So it's kind of a blind to the number of free parameters that a model has. And as more negative this value is, the better the fit. And so what we can see here is that for the dense old Aspen site, the zenith, the clumping index with zenith variation is really important. It gives us a much better agreement than the homogeneous case in black or the one that doesn't consider variation, zenith variation. And for the Blue Oak Savanna, we also see that considering zenith angle it's somewhat a better fit, but less so than the dense site. So now that we derived clumping index values, we are going to calculate FAPAR. So what we did was, now we know what clumping index looks like for these two sites, right? And we used a land surface model, JULES, which is the land component of the UKSM, the British Earth System Model, to calculate FAPAR for both sides. So when we calculate FAPAR for the old Aspen site, we have here the two stream or JULES in this green line. And then if we just add a clumping without zenith variation, we have the red line. And if we have clumping with zenith variation, we have the yellow line. And in here, I also show the FAPAR calculated by the 3D model. And it looks a bit weird for high zenith angles. But again, remember that the size of the plot for this dense site was very small, 60 meters by 50 meters. So this is edges effect, is the effects of edges, the photons escaping the canopy or interacting in weird ways. But we can see that when we add clumping, we decrease total FAPAR. And when we add the clumping with zenith variation, we decrease it even more. Now, for the blue oak savanna, it was a much larger area, so 300 meters by 300 meters. And the 3D model agrees pretty well with the two-stream scheme. But considering zenith variation of clumping or not, doesn't seem to have a large impact for this blue oak savanna, this sparse site. Although we can see that the FAPAR is also decreasing when we consider clumping. So now that we have FAPAR and a land surface model, let's see what GPP looks like. So when we calculate now gross primary productivity for these two sites, what we see is that, and the black lines are the flux tower GPP. So what we see is that joules without clumping is this green line, and then joules with clumping, GPP goes up, right? Now, for the blue oak savanna, we don't see much variation with the clumping index. And I want to talk about this huge misbehave here. It looks like joules doesn't capture this the smooth decline in GPP. It rather gives this huge decline and then goes up. This is because joules VPD is too sensitive. So what we see is that because this is a savanna site in California, what we see is that VPD explodes and joules shuts down all the stomata, but that is not realistic. But in terms of just thinking about the variation of clumping, and we see that FAPAR was varying for both of them, but now GPP is only varying for one of them, not the other. So why is that? Yeah, sure. This one? This one. Mm-hmm. No, so our truth is the 3D model, right? So the black line, yeah. No, but no. It would be great if we had, no. Right, yeah, that's absolutely true. Thanks. So I want to go back and ask, how is that possible that we decrease FAPAR, but we increase GPP? How is that even possible? I mean, we talked at the beginning that the Farcon model is a regime, it's a co-limitation of carbon limitation and light limitation. And so if we increase FAPAR or decrease FAPAR, we would expect that GPP would respond exactly in the same direction if this site was in the light limiting regime. So the case of Tom's Ranch was that site was not in the limiting regime of photosynthesis. So that's why it doesn't matter the direction of change in FAPAR. It's not going to affect total photosynthesis. It's not in that limiting regime. Now, for the old aspen side, when we reduce FAPAR but we increase photosynthesis, what we see is, well, so we have to make this plot. So it's a vertical plot, right? The vertical layer in joules and the zenith profile. So here 1 represents the top of the canopy and 10 represents the bottom of the canopy. And what I'm doing here is showing the GPP difference. So the difference between the yellow line and the green line, okay? So what we see is that GPP is increasing in the bottom layers. And when you see a triangle here, it means that the Farquhar limiting regime also changed from a carbon limited to a light limited regime, and the opposite at the top of the canopy. So basically adding clumping to joules is doing the following, is decreasing the effective LAI along the canopy. So it is allowing more radiation to go through into deeper layers that before were in the shade and now are being illuminated. So the photosynthetic capacity of this, not the photosynthetic capacity, but the actual photosynthesis of these bottom layers goes up. So although the total FAPAR of the canopy decreases, the total GPP increases because of this layered behavior in joules. So again, we go back to the discussion that a leaf, it's not a canopy. And so when people got really happy with the Farquhar model in the 80s because it was the first nice ecophysiology model that we can actually give environmental variables and give us a net CO2 assimilation back. And it was the perfect candidate to couple to these land surface models and see what was happening to them. However, people have the same model, the same Farquhar model, but apparently they're doing different things with it. And I really like this figure from Rogers et al. 2017 that shows the light response for a number of different land surface models. For a leaf here on top, and for a canopy of LAI equals 3 at the bottom. And we see that although all these models here use the Farquhar model, they are all representing different things, different values for net CO2 assimilation, not only for a leaf, but for the canopy. And why is that? How do we see that? First, we need to ask ourselves, are we modeling the same thing? So I like this picture from Anthony Walker because it shows the canopy representation of different land surface models. So if you see two colors, it means that this specific model separates sunlit and shaded leaves. Then if you see only one color, it doesn't. Then if you see all these horizontal lines here, it means that the canopy is a multi-layer canopy in radiative terms. So it's a leaf on top of a leaf, right? So joules would be something like Teco, would be something like this, where we have 10 layers and we have differences between sunlit and shaded leaves. But then you can have a number of other things that are represented in some models but are not represented in others. For example, this tiny square here means that the model takes into account some sort of understory. Others don't. Then, and I'm only talking about the canopy radiative part, but if you think about soil layers, root distribution, and so on, nitrogen consideration or not, and so on. So it comes down to these models are using the FARCO model, or as Dave Schimmel used to say, people are obsessed with the FARCO model. Yes, and people are obsessed with the FARCO model because it's a good model. But how we deal with the micro decisions of the FARCO model. So what parameters do we use? How do we account for photorespiration? How to account for temperature dependencies on dark respiration, for example? Or how to account for leaf nitrogen and phosphorus? Do we calculate VC-max and J-max from these two nutrients, or we just use a lookup table to look at VC-max? Or tea acclimation, do these models have a tea acclimation, temperature acclimation, yes or no? So these are all the micro decisions. And then we have the macro decisions, where I call the macro decisions how do we scale up the FARCO model? So do we simply put a leaf on top of another? Or how do we go from a leaf to a canopy? And as we can see, all these models are trying to go from a leaf to a canopy. Some of them use the sunlit and shaded. Some of them use a layered canopy. And so the macro decisions also differ among these models. So when we look at the clumping impacts, right? Because we just saw the clumping impact for a single flux tower site. Now, what would happen if we try now to calculate the impact of clumping, or more, if we say that clumping is some sort of a structure, this gappiness of a canopy, how does that impact global GPP? Well, and that's why I like showing these two results. So this paper was published by Jin Chang in 2012, and it basically shows GPP, the difference in GPP for BEPS with clumping and without clumping. And so when Jin added clumping into BEPS, he saw a decrease in total GPP, in total global GPP, in 12 petagrams of carbon. Now, I performed this exercise 7 years later, but now with joules, right? And Jin is also a co-author in this paper. And we see the exact opposite behavior. So when we add clumping, we increase global GPP. So why is that? Well, that is because BEPS is a canopy like this one. So GPP is proportional to FAPA somehow, is related to FAPA. So if you put up FAPA up or down, GPP will respond in the same way. Now, joules is a multi-layer canopy. So what happens is that joules is somehow related to the sum of GPPs in different layers. And then these GPPs in different layers are proportional to the FA part in these layers. So when you add gaps, you change the illumination. So although the global FA part goes down, the global GPP goes up. So what is next? So some people say, well, more data will solve this problem. But will really? And then I like this paper here, where the authors say that Earth system models disagree wildly about the magnitude and frequency of carbon climate feedbacks, events, and data to this point have been astonishingly ineffective at reducing this uncertainty. So what the authors are saying is that no, data is not helping Earth system modelers until now, or it looks like it's not. But this same like Deishima was here and there, but what we have now is that we need more data, and we are working towards getting more data. So data. So we have this unbalanced coverage in flux towers across the world. So we need more flux tower sites, across the Americas and Africa, and more in the tropical forest to really understand what's going on. but also the fact that we are living in a very exciting era now, where we can actually have flux towers from space, where we can actually measure proxies of GPP through SIF, and we can actually measure some components of Canopy architecture with the Jedi. And SPG coming on, we will be able to actually understand radiative transfer in multiple wavebands and come up with plant functional traits and all the other things. But more than only having just more and more data, we need to understand uncertainty in this data and what we need to do to reduce uncertainty, and how do we bridge an in situ measurement with a flux tower from the sky. And this is a completely open question. In terms of models, will more models solve the problem? Well, it doesn't look like it, because the CMIP simulations were like CMIP 4, no agreement, CMIP 5, no agreement. Now, earlier this year, it doesn't look CMIP 6 models are agreeing either. So should we just keep adding more and more processes and more models into it? Probably not. I mean, what we should do, more models are welcome and they will always be. But what we should do is really to revisit these models that we are actually working with them for so long, and ask the questions, are the basic theories right? Or are the way we couple one theory to another appropriate? And so the idea is that we need models that are simple as a belief, but efficient. We also need individual based models so we can ask questions about how these big leaf models are doing something wrong. But now there's also a boost, like a huge investment on demography vegetation models with ED2 and FATES being coupled into CLM. So maybe with new theory or new ways to see structure and modeling, we might come up with a better answer. But also benchmarking. Not only sit on top of your model or your submodel, your process, and think that's amazing, you publish your paper, great. No, benchmarking is essential. We should put one model next to one another, next to each other, and compare it with some sort of data sets. So that's why I show here the ILAMB table, where we have a number of different data-derived parameters, variables, and we compare our system models. And then we can understand why is this model acting so badly for that data, but so good for that other data. So we can actually be comparing apples to apples. And finally, I want to show you this idea, this figure here that I adapted from Tapio Schneider. There, it basically shows the idea of a new generation Earth system model, or what would that look like. So now we have lots and lots of good Earth observation. So things like Jedi, for example, that gives us idea about direct transmittance and some sort of canopy structure. We then use this data to feed models, complex models, high-level models, and simulate and perform. And then when we go to the global picture into these Earth system models, we can understand where we are doing wrong and where we are doing right. Because if you remember the Farquhar model, if the Farquhar model works so well for a leaf, and the two-stream is getting the FA par right, why is canopy photosynthesis not agreeing with that? So where are these two models or the data miscommunicating? And so when we answer these questions, we can go back and say, oh, okay, so what type of new Earth observations do we need? What do we need to look for? And so that's why I like to finish with a quote from Gordon Bona that says that the path forwards requires a new generation of interdisciplinary Earth system scientists who combine theory, modeling, observations and data analysis without discipline chauvinism, because we already have a lot of chauvinism in the world and we don't need anymore. Thank you. Hi, Josh. Mm-hmm. How good is good enough? I think that, well, let's think about FA par, which is a single example, but we can think about any variable really. When we compare what the two-stream model is doing with FA par, and we add, either 3D modeling as our truth or observations as our truth, we know it's wrong. But we keep playing with this, like people know it's wrong. People know canopy structure is impacting FA par, but people are not going one step back and saying, okay, guys, FA par is wrong. So probably GPP is also wrong because it's the driving force of GPP. And then the idea is, my point was not to carry on with errors that we know of. And of course, we are never know all errors. And, if it's mismatching the data, it doesn't necessarily mean that our data is wrong. It may be our theory is wrong. But I think good would be good enough when when all models are kind of agreeing, at least in the sign of the land uptake by the end of the century. Because if we disagree even in that, it means that we have a systematic problem. Like we don't even know what the land surface will be doing in those terms. Yeah, it's complex. But yeah, I also don't know how much is good enough. Hi, Nancy. Yes. Yeah, absolutely. And the another thing that I didn't mention for the sake of time, of course, but these land surface models, they work as you well said in two broadbands, right? So we don't even know what is happening with the blue versus red absorption. And when we average out an FA par and we deal with radiation as it was this, two broad bands, when in reality we know it's not, right? So that's why I think missions like the SBG, or for example, now the Klima model is the land component of the Klima model is hyperspectral. So now with a hyperspectral land surface model and a radiated transfer scheme, we can ask actually these questions. Okay, if we add clumping to make FA par, and FA par is something between 400 nanometers and 700 nanometers, where we are going in the right direction and where we are going in the wrong direction and why. So complexity is not bad in itself. I mean, we need complexity to kind of dive deep into these questions, I think. Hi. Mm-hmm. Yes. No, that's a great question, and I totally agree with you. I mean, but I don't know. And as you said, it is a kind of a philosophical question. Sometimes, as a scientist, I have the impression that we are always looking forward. And for example, when the greening of the Earth system models happen, and people need something fast and efficient to give land photosynthesis, we kind of like, oh, okay, this question is solved, next one. While in reality, it's beneficial to go back to old data, you know what I mean. But go back to theory and go back to data and ask the questions. Okay, have we looked for all the aspects of this data in theory? Are we actually satisfied and content before moving forward? And then there's this weird term, moving forward. But for example, in my case, in the example I wanted to show digital hemispherical photography which is something relatively cheap, right? You just need a good camera and good fisheye lenses, and you just need to go to the field. And then on the other hand, you have a lidar, you have a plane flying a very expensive instrument over a forest. At the end of the day, you get the same P gap, right? And so I guess we like technology and we are always asking new questions, and that is good. But that doesn't necessarily mean that we have to forget the old ones and the old pieces of data that is sitting there. I totally agree with you. Hi. 18. Yeah, sure. 18. This one? Mm-hmm. If everything goes the same and the tree goes taller, I think, I don't know for sure, but let's say that the trees are going towards the zenith here, right? Which is the center of the picture. We would have more trees, so less P gap. And then what we would see is that the two-stream scheme would be doing a better job than it's actually doing for a sparse canopy. So the clumping will go towards the homogeneous case. I assume that. What do you mean LAI is not changing? Well, if the tree is growing, LAI is changing. Right. Yeah, that is actually, that's a good question. I don't know. I don't know what would happen. That's definitely an exercise we could perform with some of these models. We get a 3D model, we grow the tree. And some papers talk about the ratio of height and width of a tree, and that the importance of clumping, or how, if clumping is a heterogeneous, if it's clumping is far away from the homogeneous case, depends on this ratio. But I haven't looked into that. But that would be definitely an interesting question to look at next time. And because I didn't have much time to talk about it, and the model I was comparing was the one that follows zenith angle and the one that doesn't follow zenith angle. But the one that follows is basically two parameters that you fit, right? You fit to your data. So that means that we would have to fit all clumping index in the world to some sort of p-gap values. Could be Jedi, for example. But another question that would be interesting is, can we find a physical equation that accurately prescribes clumping index? Because if we realize that tree height and tree width, this ratio is some sort of proportional to clumping index, we could use that instead, right? Than using p-gap. But yeah, there are lots of space to be explored there, and I don't know the right answer really. Mm-hmm. Mm-hmm. Right. No, and that is great. I mean, one of the one you mentioned, Niemeyer, I kind of tested in my PhD, and I compared that with the Remy experiments. But I remember that specific clumping parameterization didn't vary because if I remember well, the LAI also was changing with canopy density. So at the end, the higher LAI and the higher canopy density cancel out the effect on clumping. And when we look at the sparse, median, and dense, the clumping index was held constant. So that's why we kind of decided to drop that off. But yeah, definitely, like we tried to look into that, but that's why we thought it's in my dissertation chapter. Yeah, it's not published. Yeah, cool, sure. Oh, it's all. So we did that for hypothetical forest canopies. So balls, randomly distributed vegetation balls, fluctuating on space. Well, yeah, kind of. But yeah. No, yeah, but I would be happy to chat more about that. Like, uh, mm-hmm. Hi. Right. No, no chlorophyll. So again, if we go back to this image, the assumption that a nerve system model does for a canopy is something like this, right? So there's no difference between trunks or stems or anything. It's just plants, right? And then, of course, some models like CLM, for example, has a sort of a parameterization that deals with, it says, oh, a part of LAI is due to leaves or photosynthetically active surfaces. But, a fixed part of that is woody, is woody canopy. So, it tries to account for that, but actually the radiative transfer model doesn't see any of that. It really just thinks about the canopy as this glue of vegetative material. And so when we talk about FA part in our system models, we are talking about the fraction of absorbed photosynthetically active radiation for the whole canopy. So wood, stem, blah, 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 blah. So that's why, and I totally agree with you. And I mean, that's why with models like Prospect now, we can go from leaf chlorophyll content to leaf spectral properties and then rerun this radiative transfer model to see the impact of chlorophyll content on a hyperspectral PAR, for example. But none of these Earth system models do that. It's really rough. Yeah. Thank you, Brennan. Thanks, Brennan.